All right, okay, so welcome back to those of you who made it back safely from the glacier. So I'm now going to talk about the sixth part of this course, and this is progenitors and the ignition of thermonuclear supernova explosions. So far we've just talked about that white dwarfs may be the objects that explode in a thermonuclear way to form type 1a supernovae, but we have not actually looked into what the progenitor system is and how the white dwarf actually gets to an explosive state. So this is actually the topic for today. So how does the white dwarf reach an explosive state, and how does it actually ignite the explosion? All right, so this is the lecture topics I want to cover. The type 1a supernova progenitor problem is something I want to briefly review from a theorist's perspective. Then I will talk about white dwarfs as progenitors of thermonuclear explosions. We will take a look at the ignition conditions and processes. We will then briefly review the evolution of potential type 1a supernova progenitors, and then finally I want to say some words about theoretical predictions of rates and delay times and how they constrain the explosion scenarios. Now, the type 1a supernova progenitor problem, this is something we already discussed. Progenitors of type 1a supernovae have not been identified for other classes of supernovae. We know what the progenitors are. So for Kokolab supernovae, there is a handful of candidates or handful of identifications of the stars that exploded as a Kokolab supernova. So this is not the case for type 1a supernova here. We don't have any direct observation of the progenitor system. The events themselves are bright and can be well observed. However, the progenitors are faint, and so all we have so far from nearby events are non-detections and upper limits on the brightness of the progenitors. Okay, so this is something that requires, of course, some also discussion from the observational side of view. From the observational side. So here I was actually hoping for Alicia's lecture, but as a theorist you should never rely on an observer, apparently. So I will actually try to actually now do a little bit from the theoretical model building side of aspects of the progenitor problem. Okay, so what are the theory questions that are related to this progenitor problem? Well, first of all, we should establish whether a white dwarf star can actually undergo explosive burning. Then, how does the star reach an explosive state? What does a particular progenitor scenario imply for the expected rates and delay times? How does the explosive thermonuclear burning ignite? And these are the questions that actually a theorist would ask when looking at the progenitor scenarios. Now, the progenitor itself has, of course, tremendous implications for the modeling, because, as we discussed, we model thermonuclear supernova explosions in terms of the equations of fluid dynamics with additional source terms. Now, the mathematical structure of these equations, that's also something I have already mentioning before, is that they are hyperbolic partial differential equations, and for practical purposes this means that the solution requires initial conditions. Now, since the progenitor is unknown, these initial conditions are not fixed, and therefore we have to determine them somehow from some theoretical considerations. This is a side remark. Even if Alicia would have been here and told us what the progenitors of type 1a supernovae were, then we still would not be happy as theorists, because then we know what kind of star this is, but this does not tell us something about the internal structure of the star. So we still have to model the structure of the star. We still rely on stellar evolution modeling, on stellar structure modeling, and we have still to model the ignition process for the thermonuclear burning. So an observational identification of the progenitor of type 1a supernovae would, of course, then somewhat restrict the parameter space and the possibilities, but it would not fully solve the problem that we have. All right, now, white dwarfs as progenitors of thermonuclear explosions. So what do we actually have as requirements that we get a thermonuclear explosion? Well, first of all, of course, the energy reservoir should be sufficient, and second, the energy must be released on very short timescales to get an explosion. As both aspects are fulfilled for white dwarfs, we do have a sufficient energy reservoir, so this is also something we discussed before. So if the nuclear energy source for a white dwarf was truly extinct, then these objects, because they are stabilized by the Fermi pressure of the degenerate electron gas, would be stable for eternity. But white dwarfs form so that they mostly consist of carbon, oxygen, and neon, perhaps. So all these elements can be burned to iron group and release energy. So the progenitor and ignition question therefore is how can we re-invoke the nuclear life of a white dwarf star, and how does it reach the conditions to ignite nuclear burning. The second is explosive thermonuclear burning. So explosive thermonuclear burning requires degeneracy. This is what we find in white dwarf stars, and therefore the burning actually gets explosive. So we start out with the ignition. White dwarfs are most commonly composed of carbon and oxygen, so the ignition will start out with carbon-carbon fusion. So carbon-carbon fusion is a heavy ion reaction, and therefore we have a strong temperature sensitivity of the reaction rate. And it's estimated that at a temperature of about 10 gigakelvin or so, the reaction rate of carbon fusion scales with the 20th power of temperature. So the combination of these two aspects, the degeneracy of the material and the strong dependency of the ignition reaction, the carbon fusion, gives rise to a thermonuclear runaway. So this is a consequence of the degeneracy of white dwarf matter. We have no expansion and cooling in response to heat release. So normal stars are described by an ideal gas equation of state. So here, when we increase the temperature, the pressure would go up, and then we have an expansion of the star. In white dwarfs, we have degenerate matter. We discussed the equation of state before. Pressure is not a function of temperature, and therefore we have no expansion when the stellar material is heated up in a white dwarf. So therefore, in white dwarfs, the usual self-regulation of the stellar nuclear reactor, as it's sometimes called, does not work. So usually what one has is that one increases the temperature and then the star then expands and cools, and the reaction are regulated in this way. In a white dwarf, if we increase the temperature, then we have no cooling by expansion, but a strong increase of the reaction rate, because the reaction rate is so sensitive to temperature. And that, of course, then releases more energy, and we have a further increase in temperature, and this then actually makes the reaction rate even faster, so that we finally, by this self-accelerating cycle, get a thermonuclear runaway, which implies an unlimited growth of the reaction rate until the fuel is exhausted or the degeneracy of the material is lifted. Now this thermonuclear runaway ignites the explosion, but it's first of all in the first place it's a local phenomenon. The energy from the reaction in the thermonuclear runaway is transported away in a realistic medium by conduction or by hydrodynamical effects. And this leads to the formation of a combustion wave, as we discussed it a couple of lectures ago. So therefore, we have a fast spread of the explosive reactions. And even in the case of the combustion wave being a slow subsonic deflagration, it is accelerated by hydrodynamical instabilities. So therefore, in any case, either as a turbulent deflagration or as a supersonic detonation, the burning will spread out very quickly. And this actually makes the explosion going. So the nuclear timescales for the burning are very short, on the order of the dynamical timescale of the system. So therefore, we expect a strong interaction between the reactions and the hydrodynamical flows, and this is actually what you would call then explosive burning. So in this way, we have established that in a white dwarf, we can actually have explosive burning. So what white dwarfs make type 1a supernovae? Well, white dwarfs are, of course, as you know, the endpoints of evolution of light stars. And the composition of such a white dwarf depends on the stellar mass of the progenitor. So it can be helium, carbon, oxygen, or oxygen neon, depending on how massive the 0H main sequence star that then finally formed the white dwarf was. The favorite scenario is for type 1a supernovae the explosion of a carbon-oxygen white dwarf. Why is this? Well, first of all, this is the most likely outcome from stellar evolution. So most stars will actually produce carbon-oxygen white dwarfs. The second is that the thermonuclear burning is likely to produce a type 1a supernova-like event. So we discussed the nuclear reactions, and these actually can produce the elements that we see in the spectra of type 1a supernovae. Why not helium white dwarfs? Well, first of all, if you have an explosion of a helium white dwarf, you would perhaps also expect to see some helium in the spectra. And this is excluded for type 1a supernovae. Then there's another nuclear synthesis argument. So helium burning, of course, releases a lot of energy, so it's easy to burn to nuclear statistical equilibrium in this case. So iron group elements would be produced, but little intermediate mass elements. So therefore, such events, if they existed, would lack intermediate mass elements and therefore not show the typical silicon and sulfur and so on in their spectra. What about oxygen neon white dwarfs? Well, the traditional picture until a couple of years ago was that these would produce core collapse supernovae. And this is induced by electron captures on the material on magnesium-24 or neon-20 before the explosive burning ignites. In principle, they could also, of course, undergo burning and release energy and therefore explode in a thermonuclear explosion. But here it was thought that before that actually happens, the electron captures lead to a reduction of the pressure so that the star collapses rather than undergoing a thermonuclear explosion. However, recently, Sam Jones has looked into this again, and he found that actually very high central densities are needed in order to get this gravitational collapse going. What you find for moderate densities is rather a thermonuclear explosion. So he actually did some 3D simulations of thermonuclear burning in oxygen neon white dwarfs. And what he found is that, in particular, if you do these simulations in multi-D, because of the flame instabilities that you have, the flame accelerates so quickly that it actually releases enough energy that a thermonuclear burning event, thermonuclear explosion event is more likely than an electron capture supernova. So this was actually also performed with our supernova code. Only for the very highest densities, this is this case here, you actually can suppress the growth of the radial instability because of the fire polishing lengths becoming so large then. So therefore, burning does not really get turbulent, and then you get a collapse to a neutron star. But this actually requires central densities above 10 to the 10 grams per cube centimeters. So therefore, in principle, oxygen neon white dwarfs are also a candidate for forming thermonuclear supernova explosions. If they actually existed, if a detonation in such a oxygen neon white dwarf would ignite, what would it look like? So this actually was also studied, and indeed this would produce an event that is not very unlike a type 1a supernova. But this is a detonation we looked at here. So the question is, can a detonation, so what Sam Jones looked into was deflagrations. The question here is, can a detonation trigger an oxygen neon material? This is still an unanswered question because resolving this in a numerical simulation was very hard. So we tried, but we did not actually get a conclusive answer. In any case, however, you would expect that oxygen neon white dwarfs are less abundant than carbon-oxygen white dwarfs. So if these actually contribute to type 1a supernovae, then it would be only a small fraction. Recently, people have also discussed a variant of this scenario, which is hybrid white dwarfs consisting of carbon, oxygen, and neon. So the idea here is that carbon burning starts off-center in the core of an AGB star, but burning does not reach the center, so that in the center you have unburned carbon left behind, surrounded by a layer of neon-rich material. So we also looked into explosions of these events. So that's an interesting case. However, whether or not these exist is still unclear. The prediction of these oxygen neon, carbon-oxygen neon white dwarfs, hybrid white dwarfs to exist depends strongly on assumptions on mixing made in the 1D stellar evolution calculations that concluded that they may exist. So this is rather uncertain. Okay. Okay, so carbon oxygen white dwarf are the most likely progenitors of type 1a supernovae. Now we have to think about how these actually ignite. Well, white dwarfs are inert objects. A single white dwarf is the endpoint of evolution. However, white dwarfs and binaries are not. So therefore, several scenarios were suggested where a white dwarf in a binary can actually trigger thermonuclear burning. But none of these scenarios is established beyond doubt. Okay, so Chandrasekhar mass explosions. Well, one obvious way to get a white dwarf to an unstable situation that could perhaps trigger burning is actually that you grow the mass of the white dwarf to the Chandrasekhar mass, to the limit of its stability. So this can be achieved, for instance, by accretion of material from a binary companion. Now this has been a very popular scenario, the Chandrasekhar mass explosions of white dwarfs, as a model for type 1a supernovae, because it seems to be a natural explanation for the type 1a supernova homogeneity, because there's always the same amount of fuel 1.4 solar masses available for each event. So this is one reason. The other reason is that approaching the Chandrasekhar mass, the radius of the white dwarf will go down and the central density will go up. So therefore, it's unavoidable to actually reach the conditions for triggering carbon burning. So how does carbon burning ignite? Well, the details of this is rather complex and involved. I just want to mention some of the problems here. This is discussed in more detail, for instance, in this paper by Gasquez and collaborators. So here's the temperature log density plane, and the ignition curves are shown here. And what you see is that in this paper, actually, a variety of different ignition curves are considered, and the uncertainties that you have here are because the reaction rate depends on the state of the plasma. So this sets the condition for the penetration of the Coulomb barrier that's necessary to fuse the nuclei. At high temperatures and low densities, the ions form a Boltzmann gas, and then the rate of fusion depends on the thermal energy of the ions, and this is the regime of thermonuclear reactions. So this is rather well understood, but at lower temperatures and higher densities, the plasma becomes a strongly coupled Coulomb system, can be liquid or solid. And these effects then introduce uncertainties into the possibility to fuse, or what thermodynamic conditions would be required to fuse carbon. Now, the effect that counteracts the burning or the ignition of burning is cooling. Cooling happens by neutrinos, so energy is carried away from a white dwarf that contracts and heats up in its center to finally ignite carbon burning. The counteracting effect is that it will actually also cool by emitting neutrinos. The neutrinos are formed either in plasmon decay or in electronucleus Bremsstrahlung, and only when the energy generation due to the carbon reactions balances the neutrino loss, one can really speak of an ignition of the burning. Okay, now in the regime we are interested in, so at say densities of a few times 10 to the 9 grams per cube centimeters, as we find in the centers of Chandrasekhar mass, white dwarfs, and temperatures of the order of 10 to the 8 Kelvin, we are in the intermediate so-called thermonuclear reaction regime. So we actually approach the ignition curves from this direction. So not only temperature but also density effects play a role. So the reaction rate then appreciably depends on the density. So that means when the central density goes up, then we approach the carbon ignition curve. And the energetic evolution of the white dwarf core is then dominated by the compression and heating and the cooling due to the neutrinos. And when reaching a central density of about 2 times 10 to the 9 grams per cube centimeters, the nuclear energy generation due to carbon burning finally is believed to win over the neutrino cooling, and then carbon burning commences. Okay, so this is how carbon burning ignites. But this is not yet really the onset of the actual thermonuclear explosion, because after ignition of carbon burning, energy can still be transported away from the center of the white dwarf star by convective motions. Now, in this stage, a highly turbulent flow of highly turbulent convective motions will develop, and only after a century of this so-called simmering of convective carbon burning, you expect hotspots to form in this very turbulent environment, and these then undergo thermonuclear runaway and lead to a flame formation. Now this is an additional complication, because this means the exact geometry in which the flame ignites is set by highly nonlinear hydrodynamical effects by turbulent convection. And this is very hard to follow numerically or in a theoretical model. So this is then the question of geometry of flame ignition. Well, this is one of the most fundamental parameters actually for the models. It has fundamental impact on the strength of the explosion. The questions that are important here, or are decisive, are whether or not the ignition happens really at the center of the white dwarf or slightly off-center. If off-center, how far off-center, and whether or not it ignites in many ignition sparks, or whether it ignites only in one place. Now, this can introduce substantial asymmetries in the burning, in the flame evolution, and the nonlinear instabilities will amplify these effects, and therefore this will have a fundamental impact on the strength of the burning. Now, therefore, people have looked into this, and Mike Zingali in Sterling book performed numerical simulations of the convective carbon burning prior to ignition, so the simmering phase inside the core or near the center of a carbon-oxygen white dwarf. He used a specialized code for this, a low Mach number anelastic code. And here's a movie of how these simulations look like. So you see these highly turbulent convective motions that develop when carbon burning goes on. One particular feature that you see here is that you have a not completely unordered structure, but sort of a bidipolar flow field. So inward and outward direction of the flows are here color-coded in blue and in red. So under these conditions, finally the flame is supposed to ignite in some part of this convective environment. And this is, of course, very hard to predict. So the current best knowledge is actually from this kind of simulation I've just shown, performed by Mike Zingali and collaborators. So the latest publication about this was by Nonaka in 2012. And they actually favor, in their simulations, or the simulations favor an off-center ignition at a radius of about 50 kilometers, or 50 kilometers out of the center of the white dwarf star. And they find that a nearly simultaneous thermonuclear runaway in multiple locations is not very likely. So that means that according to these simulations, a single spot asymmetric ignition is very likely. One has to keep in mind, however, that the situation that they simulate here is not the ones that should be realistic for convective carbon burning in the center of a white dwarf star, because this actually was performed with a numerical code, and the Reynolds numbers reached here are, of course, far away from the realistic situation. So the question is how realistic this is. This is actually the solution you get for only very mild turbulence. And this is, of course, not the realistic simulation. But this is actually the best knowledge we have on the ignition geometry today. So what about subchandrasekhar mass white dwarfs? Can they also undergo an explosion? Can they trigger an explosion? So this was for a very long time not the favorite model. However, and the reason for this is that in subchandrasekhar mass white dwarfs, an ignition seems less natural than in a Chandrasekhar mass white dwarf. So Chandrasekhar mass, approaching the Chandrasekhar mass, you will at some point, because of compression, always intersect with the carbon ignition curve, and therefore carbon will start burning. And a subchandrasekhar mass white dwarf doesn't do that naturally. However, there's a promising feature of subchandrasekhar mass white dwarfs, and this is that the density structure is less compact. So that means that detonations in principle can produce intermediate mass elements as well, and therefore lead to a composition of the ejecta that produces observables that resemble observed type 1a supernovae. So we'll discuss this in more detail when we speak about the explosion scenarios tomorrow. So this, however, is a promising scenario. But then the question, of course, arises how to ignite a detonation in such a subchannel cycle mass white dwarf. Deflagrations, of course, are not expected here, but a detonation could lead to something like a thermonuclear, like a type 1a supernova. So therefore, the question, how to ignite a detonation? Well, also the ignition of a detonation is a very complex process in detail. It requires also a thermonuclear runaway, but in this situation, a shock wave must form as well, because the detonation, as we discussed yesterday, is a mode of combustion wave propagation that is supported by a shock wave. So that means that in principle you would expect that the burning front has to be initiated with supersonic velocities. The shock wave compresses the fuel and the burning releases energy. This energy is then needed in turn to sustain the shock wave. So therefore there's a delicate interdependence between the shock wave and the burning, and one has to ensure that the shock and the burning front don't de-align, because then the detonation will fizzle out and not propagate. Okay, so the details of detonation ignition are theoretically not well understood. There's still theoretical and experimental research ongoing on these topics, but in principle you could imagine two fundamentally different ignition processes that could lead to a detonation. One is a direct ignition. So this relies on the pre-existence of a strong shock wave. This strong shock wave is then thought to propagate into the fuel, and if its velocity exceeds the Chapman gauge speed in the flow in the fuel material, then a detonation forms by some kind of relaxation process under appropriate conditions. The other scenario, so in most cases actually we don't expect to have a strong shock wave. The more relevant scenario perhaps therefore for us for triggering detonations in white dwarfs is spontaneous ignition. So here the ignition of a detonation is thought to proceed under in an initially shock-free environment. So this requires a specific preconditioning of the thermal properties of the fuel. So the idea is the following. Reactions have certain self-ignition delay times. This is called induction time. So the delay time of material when it's heated up to really set off a reaction is called induction time, and this induction time depends on the on the temperature of the fuel. So therefore, Zeldovich in the 1970s came up with the idea that you could arrange the temperature profile inside a fuel material such that you have a very shallow temperature gradient. So that means that you have subsequent self-ignition along that gradient, but since this gradient is very shallow, it will happen quickly in one place after another. So therefore, you can reach a supersonic phase velocity of the self-ignition. And therefore, a supersonic reaction wave will result from this. Now this can, if the setup is appropriately prepared, transition into a detonation once the reaction wave reaches the Chapman gauge speed of the fuel. So this is just a basic picture. Reality is more complicated here because of the energy release in the reactions. You have hydrodynamical effects that are excited by that, and the generalization of this Zeldovich gradient mechanism to include nonlinear hydrodynamical effects is called shock wave amplification through coherent energy release, or SWACER, and this is sort of the general idea of how a detonation could perhaps trigger in white dwarf material. The problem with this is that the processes that actually lead to such a self-ignition of a detonation are not resolvable in simulations that involve the entire white dwarf star. So you can estimate that it would be necessary to capture the carbon burning length scale, which is a few centimeters under the densities we are interested in, and this would have to be captured. This would have to be captured with about 40 grid cells or so to really resolve the carbon burning ignition. And this is impossible, of course, if we want to capture the entire, or if we want to accommodate the entire white dwarf star on our simulation grid. So therefore, it is not reachable in the foreseeable future to resolve really the ignition of a detonation in a thermonuclear supernova explosion. So all what we have at the moment is numerical simulations that determine in small-scale offline simulations the minimal values for density and temperatures at which such an initiation of a detonation is still possible. But this is then in the end just sort of a hand-waving argument and an estimate. Okay, so this is how deflagrations and detonations can ignite in white dwarfs. Of course, we still have to provide scenarios for how this happens, especially in the subchandler Sekar mass white dwarfs, to trigger a detonation. So thermodynamic conditions for a detonation ignitions are not spontaneously met in subchandler Sekar mass white dwarfs. So therefore, for a sort of violent interaction with the companion star is required. And for that, several possibilities have been suggested. The first is just a direct collision of two white dwarfs. You smash two white dwarfs onto each other, and this is then thought to give rise to a strong shock wave. And in this case, you could have a direct ignition of the detonation. Now, this scenario that we actually collide two white dwarfs head-on seems rather unlikely. However, recently there have been some arguments that the Kozai instability in triple systems could actually enhance the rates that are expected there, but this is still unclear. The other possibility that has been in the literature for quite a long while now is the double detonation scenario. So here the idea is that we have a subchandler Sekar mass white dwarf that accretes helium-rich material from a companion star, and this helium-rich material then builds up a layer on top of the carbon-oxygen white dwarf core. Well, the classical picture of this double detonation scenario is that the helium layer that is accreted on top of the carbon-oxygen white dwarf undergoes the ignition of a detonation once it has become massive enough. And this detonation of the helium layer would then drive a shock wave into the carbon-oxygen core and trigger a secondary detonation in that core. Here the ignition is thought to happen as a spontaneous ignition of a detonation, and this is the basic idea of the double detonation scenario. So we'll look into numerical simulations of this tomorrow. Another possibility is the merger of two white dwarfs. The violent white dwarf inspiral merger. So why actually do I list this here on the subchandler Sekar mass ignitions of detonations? Well, in a violent tidal interaction, and you can have unstable mass transfer, and before the actual merger of the white dwarfs, because of this unstable mass transfer, a detonation could be triggered. So this was actually suggested by James Guillaume, and Rüdiger Packmore looked into the merger of two carbon-oxygen white dwarfs. And here the idea is that in this final violent mass transfer due to strong tidal interaction close to the actual merger of the white dwarfs, the detonation triggers and burns then this still intact white dwarf. Now this white dwarf then has a mass that's well below the chandler Sekar mass, so therefore we in the end expect in this scenario as well a detonation in a subchandler Sekar mass white dwarf. There are different variants of this scenario, so it could potentially involve the detonation of a thin helium layer that surrounds the detonating white dwarfs, and then we would have something that's similar to the double detonation scenario. But in any case, ignition here is again expected to happen via the spontaneous detonation ignition scenario. Okay, another scenario that is discussed for thermonuclear supernova explosions, apart from the chandler Sekar mass model and subchandler Sekar mass detonations, is the chandler Sekar mass scenario. So this has not been worked out in much detail, but I want to mention it here for completeness. All this discussion was triggered by the observation of some superluminous type 1a supernovae. The prototype was found by Andy Howell in 2006, but there have been detections of some observations of a few other events since then. And the interpretation is, if you want to reach the brightness of these superluminous type 1a supernovae, then you need, by nickel 50-6 decay, then you need a huge amount of nickel 56. And this is estimated so much, close to a solar mass, that in order to produce this, you would require white dwarfs to undergo thermonuclear explosion that have substantially more than the canonical 1.4 solar masses. So therefore, superchandler second mass progenitors were suggested for these objects. So how can one form such superchandler second mass white dwarfs? Well, the original idea was perhaps by mergers, but it's not quite clear how this should happen. In principle, you could have in the merger that then completely merges the two white dwarfs a total mass that is above 1.4 solar masses, but the densities are not necessarily very high. And once an object forms in this merged object, in the merged configuration and grows in mass, it will probably trigger the explosion at the canonical Chandler second mass. So how can you support masses of white dwarfs that are above 1.4 solar masses? Well, one very straightforward way to achieve this is, of course, to include rotation. So rotation can stabilize masses above the Chandler second mass. Rigid rotation would actually increase the mass stability limit to just above 1.5 solar masses, so not by much, but by differential rotation you can actually reach masses that are on the order of 2 solar masses or so. So this is a possibility. Another possibility that has been discussed recently was extremely strong magnetic fields. So you would need white dwarfs with a surface magnetic field of 10 to the 13 Gauss or so, and then you could support rather high white dwarf masses. The Chandler second mass would be then increased to something like 2.5 or so solar masses. But this scenario is very speculative. You need very high magnetic fields in white dwarfs to achieve that. Okay, so these are in the potential white dwarfs or configurations of white dwarfs that can undergo the triggering of a thermonuclear supernova. Of course, the question is, how do we actually evolve stellar systems into these white dwarfs to trigger a thermonuclear supernova? So stellar evolution channels have been studied as progenitor scenarios for type 1a supernovae. They all attempt to reach suitable conditions for triggering a thermonuclear explosion. In most cases, as said before, this involves interaction with a binary companion. So what one actually models here is binary stellar evolution. The goal is then of these attempts to follow the evolution of systems towards a potential ignition of a thermonuclear supernova. So the goal is to determine the realization frequency of different progenitor scenarios. And this is, of course, important if we want to combine this with predictions of that scenario for nucleosynthesis and make this an input for galactic chemical evolution calculations. So I will just give an overview here. There have been detailed reviews covering the field by Bouvang, who's here, or is he here? Oh, over there, yes. You should give this part of the talk, actually. And Danny Maus had also a recent review where he discusses mostly the observational constraints. But I want to mention, or to highlight here, that there's a modeling gap. So the last stages that actually lead then to the actual ignition cannot be followed in conventional stellar evolution calculations. So these stellar evolution calculations evolve stellar configurations to a system where one thinks that maybe a thermonuclear supernova sets off here, but this is of course not part of the evolution calculation itself and not a consistent prediction. Now, I will actually just briefly try to give an overview of the general idea here of the exploration of possibilities in binary stellar evolution that could lead to thermonuclear supernova explosions. So we start out with a main sequence binary, like here in the schematic picture. Depending on the initial separation of these two main sequence stars, narrow or wide, they may undergo a common envelope phase, as here or not. If the system is wide enough, as here in this right-hand side, then a common envelope phase is avoided and a symbiotic star forms. And here the companion of the white dwarf that is actually formed is a giant, and the idea is that by wind accretion from the giant onto the white dwarf, one could perhaps reach conditions for a thermonuclear supernova explosion. So this is scenario E here. However, it's not expected that this is a huge contribution to type 1a supernovae from this scenario, from the symbiotic star scenario, because the accretion in principle would have to start out with a white dwarf of about 0.6 solar masses. We consider a wide binary here, so therefore the evolution of the components is virtually independent of each other. So therefore you would expect to get typical white dwarfs as you would see them from single star evolution as well out of such a system, and these have, as I've shown already before, typically 0.6 solar masses. Then the wind accretion is expected to be rather little efficient, so therefore growing such an 0.6 solar mass white dwarf by wind to a Chandrasekhar mass is something will be very hard. The alternative scenario for a closed binary is to go through a common envelope phase, and then in the end, after the common envelope is expelled, a closed binary is formed consisting of a white dwarf and a main sequence star. Now the main sequence star may evolve further and start to lose material in Roche lobe overflow that is then accreted onto the white dwarf. So this is this scenario here. And on the white dwarf, it's expected that the accreted material will burn steady. So therefore, the system may appear as a supersoft X-ray source. And ultimately, this accretion of material and slow burning of the material into carbon oxygen will increase the mass of the carbon oxygen white dwarf star, and a type 1a supernova may trigger when it comes close to the Chandrasekhar mass. The alternative is that the companion is a supergiant before starting the Roche lobe overflow, then a second common envelope phase is possible, as here. If the giant's core is degenerate, then in the end we will have a system that consists of two white dwarfs. And this is then the so-called double degenerate scenario, and here one expects that the system loses angular momentum by gravitational wave emission, and in the end this leads to a merger of the two white dwarfs and the type 1a supernova. So this would be scenario A. Could also be that the Roche lobe overflow from you form a helium white dwarf and a carbon and oxygen white dwarf, and then you have Roche lobe overflow from the helium white dwarf onto the carbon oxygen white dwarf. So this would appear as an AM-CVN system. In principle, you could also expect that this may give you something like a type 1a supernova explosion, perhaps in a double detonation scenario. Now, if the giant loses if the giant possesses a non-degenerate helium core, that's this case here, then in the end one forms a system consisting of a white dwarf and a helium star, and in this case then one can have the white dwarf accreting helium material and Roche lobe overflow, and again it's expected that this could lead to a type 1a supernova. So this actually is a schematic overview. Wang in his review has many other channels considered there, so there's a much wider range of possibilities here, but already this illustrates that starting out from two main sequence stars, there's a variety of type 1a supernova explosion scenarios, and both Chandrasekhar mass and sub-Chandrasekhar mass explosions are possible in this scenario. Okay. So this is what I want to highlight next. So this is sometimes a bit confused in the discussion. So there's no one-to-one correspondence in the classification of the progenitor scenarios as to whether you classify them according to the progenitor evolution, whether they are single degenerate or double degenerate systems, or as initial conditions for the explosion, where you could differentiate Chandrasekhar mass versus non-Chandrasekhar mass explosion models. So explosions of both Chandrasekhar mass and non-Chandrasekhar mass models are potentially possible for both kinds of binary systems. Now, the single degenerate channel, where we have the white dwarf accreting from a main sequence and or a red giant companion star is thought to lead perhaps to the ignition of a white dwarf when it reaches the Chandrasekhar mass. The complication, however, here is that the accretion rates in order to grow a white dwarf to Chandrasekhar mass have to be very carefully tuned in the single degenerate channel to really grow the white dwarf to Chandrasekhar mass. So the parameter space is restricted to a rather narrow window. If the accretion rates are too low, then one would expect that the material will actually cool down, become degenerate, and nova eruptions go on. And then the traditional picture would say, well, if a nova eruption happens, then the white dwarf will lose more mass in this nova eruption than it has previously accreted, and therefore this would not be a way to grow a white dwarf to Chandrasekhar mass. However, there are observations of systems, recurrent novae or RS or Fuchsius system, where the white dwarf is constrained by observations to be rather massive. So therefore, observations would indicate that still mass gain, although you have a nova eruption, is still possible. But this is theoretically not finally established. If you have too high accretion rates, then the white dwarf would not be able to accommodate all the material, so an extended helium-rich envelope will form. And for moderate accretion rates, the system will form a degenerate helium shell that can, by burning the material to helium, then you have form a degenerate helium shell, and finally a detonation in this helium shell could commence and perhaps trigger a secondary core detonation. So this happens before the Chandrasekhar mass is reached, so this in the end would lead to a soft Chandrasekhar mass explosion potentially. For somewhat higher accretion rates, one expects quite hydrostatic burning of the accreted material to carbon and oxygen, and this is actually what for a very long time was the favorite single degenerate Chandrasekhar mass scenario. So here the white dwarf would reach the Chandrasekhar mass and explode as it reaches the Chandrasekhar mass as the standard model. However, this requires a very fine tuning of the accretion rate, and it's not clear whether it's rather unlikely that because of this very fine tune, this high fine tuning that's needed for the accretion rate, that you would have a large number of objects or a large number of systems that can grow the white dwarf to the Chandrasekhar mass. So the single degenerate scenario is reflected with rather great uncertainties. Stable mass transfer to form a Chandrasekhar mass white dwarf is difficult to achieve. There is only very sparse evidence for such systems to exist. So this would actually something again for an observer to talk about. A potential problem of this scenario in principle, however, is also that the system will never be free of hydrogen and helium. And hydrogen and helium are of course not detected in spectra of type 1a supernovae, so one has to somehow find reasons why we don't see hydrogen and helium in the spectra of type 1a's if these were to explode in the single degenerate scenario. And one way to reconcile this is this spin up, spin down scenario that was suggested by Stephen Justin to explain the lack of hydrogen and helium in the single degenerate channel. So the idea here is that one has continued accretion and transfer of angular momentum, which leads to rotational support of the white dwarf star and prevents its explosion. And this actually can go on until the donor star has exhausted its hydrogen helium rich envelope, and only then the white dwarf starts to spin down again. It loses its rotational support, and this then could give rise to a type 1a supernova. Now in this scenario, of course, because you first spin up the white dwarf and support it beyond the Chandrasekhar mass, and then when the angular momentum transport ceases and the white dwarf spins down again, it will explode at some point, but this will happen at masses above the Chandrasekhar mass. So here one actually expects an explosion that's for an object that is slightly above 1.4 solar masses. And also this scenario would lead to other long delay times because of this long evolution with the rotational support. The double degenerate scenario is when two carbon-oxygen white dwarfs merge. This has been suggested already in the 1980s. The advantage of this progenitor scenario is that this system naturally doesn't contain almost any hydrogen or helium, so therefore it's no problem to give an explanation why we don't see hydrogen and helium in the spectra of type 1a supernovae if they arise from mergers of carbon-oxygen white dwarfs. However, the outcome of such a merger is highly controversial. The original model was that a Chandrasekhar mass white dwarf has to form in order to give rise to a thermonuclear explosion that produces a type 1a supernova. And this, in principle, is the original idea. Martin von Kerkwijk pointed out that it may also be possible in such a merger to trigger a detonation, perhaps in sub-Chandrasekhar mass white dwarfs. So this was actually tested in hydrodynamical simulations, which, however, did not strongly support this idea. But in any case, systems of two carbon-oxygen white dwarfs that in total have a mass above the Chandrasekhar mass and could therefore follow the original model should exist. So there are observations of potential candidates of such double degenerate scenarios with a total mass above 1.4 solar masses that would merge in less than a Hubble time. So this has been detected, so such objects actually do exist. So in the merger process, the idea is that the less massive companion star is tidally disrupted and forms an accretion disk around the primary. But then you would expect from this situation a rather high accretion rate onto the more massive carbon-oxygen white dwarf. And this high accretion rate leads to high temperatures in the places where the accretion stream hits the carbon-oxygen white dwarf, and therefore an off-center ignition of a slow burning that converts the material into oxygen and neon is expected here. Now in this case, for a very long time, the standard paradigm was that then if you actually convert the carbon-oxygen white dwarf into an oxygen-neon white dwarf, a gravitational collapse is more likely than a thermonuclear supernova explosion. So this is the accretion-induced collapse scenario. However, recent numerical simulations indicate that it's not so easy to get such an object to really collapse. Even oxygen-neon white dwarfs seem to be more likely to undergo a thermonuclear supernova explosion. Another possibility has been pointed out by Herbert Fisher and collaborators 2 years ago. So they have performed some numerical simulations of the in-spiral of the two white dwarfs in the merger, and in this accretion disk they found a spiral mode instability, and they claim that this spiral mode instability could also set appropriate conditions to trigger a thermonuclear explosion of the primary white dwarf. In these systems, however, it's also possible that due to the strong mass transfer in the in-spiral and tidal interaction phase already before the complete disruption of the secondary or shortly after it, when you can invoke a detonation, this happens before the primary actually gains mass, so it is still a sub-Chandrasekhar mass white dwarf that explodes here. So this is the idea of the violent merger scenario put forward by Rüdiger-Packmore. It has been considered in several variants, and it has been shown by numerical simulations and derivation of synthetic observables that if successful, it would actually reproduce normal type 1a supernovae rather well. The question here is how robust the ignition of the detonation in this violent merger scenario really is. The transfer from an always present thin helium layer on top of the carbon-oxygen white dwarf may help here and then make this scenario similar to a double detonation process. So finally, another explosion and ignition scenario has been suggested by Noam Soker and collaborators. This is the so-called core-degenerate merger model. So here the idea is that the merger between the two carbon-oxygen course takes place in the final stages of a common envelope episode. So then inside this common envelope is a circumbinary disk forms around this post-AGB core and the white dwarf companion. The interaction of this double white dwarf system with the circumbinary disk is supposed to lead to a merger and perhaps to a thermonuclear supernova, but the details, so this is just an idea that Noam Soker proposed, but the details have not been really worked out yet. Okay, finally a few words about rates and delay times. The occurrence rates of type 1a supernovae are observationally constrained, and we also have measurements of the distributions of delay times. So this is the time span between the formation of the progenitor and the type 1a supernova explosion. So this puts constraints on the progenitor model, and therefore the task for theory is to provide theoretical predictions for the occurrence rate and the delay times for different progenitor channels. And this is tackled with binary population synthesis calculations. So the idea here is the following. We assume a mass distribution and a distribution of initial separations between the newly formed binaries. And then one follows the evolution of these binaries, and one does so not only for one system, but for a huge set of systems. And of course, for a large number of systems, it would be very computationally demanding to follow the binary stellar evolution in detail. So therefore, what people do in binary population synthesis calculations is that they parameterize the evolution of this binary system based on pre-computed binary stellar evolution tracks. So there are some standard calculations done, and this is what people base their evolution in the population synthesis studies on. So in the end, one performs these binary population synthesis studies for two goals. One wants to predict rates and delay times. Prediction of rates seems to be the more difficult of the two problems, because not all phases in the progenitor evolution are well understood. It's not clear whether specific mechanisms, mass accretion or so on, work and lead to a successful type 1a supernova explosion. So one has to assume, for instance, that the predictions for the mass accretion rate put forward by Ken Wood and his collaborators that are necessary to reach a Chandrasekhar mass white dwarf, for instance, are correct, and then that a Chandrasekhar mass white dwarf would really produce a type 1a supernova. So therefore, binary population synthesis relies on assumptions and approximations, and therefore the predictions made by binary population synthesis are afflicted with large uncertainties. Perhaps a bit more solid is the prediction of delay times in binary population synthesis calculations, because the delay time between the formation of the star and its explosion as a supernova is usually dominated by particular physical effects that are sometimes better understood. So for producing carbon oxygen white dwarfs, the stellar evolution time is rather short, so therefore the delay time in the single degenerate scenario is dominated by the evolution time scale of the secondary, of the donor star. In the double degenerate system, we have the inspiral merger of two white dwarfs, and here the time scale is set by the angular momentum loss due to gravitational wave emission, which brings these two white dwarfs closer together so that they finally can merge. And this gravitational wave emission is associated with a time scale that is following or that is proportional to the fourth power of the orbital separation. If the scaling is unaffected, in principle, the scaling is, or the time scale for the merger would be affected by what happens in the common envelope phases. But if one assumes that no matter what the nature of this double degenerate system is, the common envelope phase always has the same effect, then one could actually go on with these rather clear predictions from gravitational wave emission, setting the time scale. If this is the same for all systems, then the merger time scale results from the product of the initial distribution distribution, which is assumed to scale with 1 over the separation, and the gravitational wave emission that goes with the 4th power of the initial separation, and therefore one would expect to have this scale with 1 over time. And this is actually, this power law scaling is something that seems to be supported by observations. So this is taken from a recent review by Danny Maus, who put together the observational measurements of the daytime distributions. And this actually seems to follow this power law shape quite nicely, which is predicted to be followed by population synthesis calculations for the double degenerate systems. Single degenerate systems, what you see here is different predictions from binary population synthesis calculations by different groups. And you see that here the uncertainties are apparently large, so the magnitude of the contribution and also the shape of the daytime distribution is very differently predicted in different calculations that are color-coded here. So there is not much of an agreement in this respect. But it seems to be that the general trend is that most binary population synthesis calculations would predict a rate for the single degenerate scenario that is too low to explain type 1a supernovae, and also the daytime distribution does not match the observations, whereas generally the daytime distribution expected from mergers seems to be supported by observations, so at least type 1As with longer delay times could be due to white dwarf mergers. Okay, so that's it for today. Thank you very much for your attention. More on explosion scenarios tomorrow.
Just for this last graph here, if I see then the delay times coming up always at a flu time spent in 7 years. If I look at both plots.
Here?
Yeah.
So the question is, what is the short?
Is for galactic chemical evolution isn't that too early in order to only go out at velocities of -1?
Yeah. Sure. I mean, this would be, yeah. I mean, but this is actually, I mean, this is what actually is suggested by the observations, first of all, right? I mean, this is not just a theoretical prediction, but you actually have measurement points here. And actually for the progenitor type 1a supernova business, the harder question is actually to explain the short delay times, because the long delay times seem to be matched well by the double degenerate scenario, but this will not produce actually, or is unlikely to produce the prompt explosions. So therefore, so this seems to be the harder problem. Whether or not this is consistent with galactic chemical evolution, I don't know actually. So people have now put in proposals to study this in more detail, but yeah, okay. Yeah.
Question? Yeah. First, actually, I have a question about this plot because I'm trying to find the same, and it seems to be that something wrong with axis, because these points from Tatani 2008 to 9, as I remember correctly, they started from 1 billion year.
This year, right?
Yes.
Okay.
So they started from 1 billion, and usually when I saw the plots like this, so it looks like you have this prompt. So it's in one scale, so both plots in one, and so this prompt, how's it, prompt delay time? It usually works on the earliest time up to before 1 billion year, and it's higher than this delayed. I mean, like.
Yeah, that's right. I mean, this is why people say, well, there must be a prompt channel and it's a separate
so
long delay time channel. Yeah, sure.
You know, like this one, and then. Something like this.
That does not actually match here, right? So I don't know what actually. So the prompt channel that people predict is, but that's usually from the system of a white dwarf and helium companion, right? helium star, companion star.
Single.
Yeah, from single degenerate, but some people actually then say, well, the most likely here is a helium companion star, right? Helium star is a companion in a single degenerate scenario. But anyway, yeah, so I've just taken this, so I took this out yesterday night from the paper, so.
And
At least the version of the paper I have is actually with these axes.
Then I wanted to ask about anisotropy of explosion.
Yes.
Can we distinguish the different progenitor system like single degeneration and double degeneration using some polarization observations?
Yes, I mean this is one thing that is tried, and indeed, so these explosions. So the plan was to talk about this a bit more on Saturday. So the explosion mechanism predict rather different degrees of asymmetries. So you would actually expect that in a merger of two white dwarfs, because you have sort of this preferred plane and rotation axis, you would actually have a huge asymmetry, and this can actually would be a prediction from this scenario. So there have been a few calculations, radiative transfer calculations, to determine the polarization signal, also from some of our models, from a merger model, from a sub-Chandrasekhar mass model, and from a delayed detonation model in the Chandrasekhar mass scenario. It seems that the double detonation sub-Chandrasekhar mass explosions and Chandrasekhar mass delayed detonation, so the standard scenarios, actually are rather spherical and produce polarization signals that look like the observations. The one merger that was tested did not, but this actually with the mergers, so this was a violent merger of Rüdiger-Packmore, an early version where he actually assumed that both white dwarfs would explode. But this is not clear. In the violent merger, it's also possible that only one of the cores explodes and the other not. And then, of course, you would also expect a rather spherical object. So it depends on, but in principle, you could, yeah, I mean, you're right. Based on the polarization measurements, you actually get information on the geometry of the event, and this is
theoretical calculations. So, what they provide, what degree, like 2%, 3%?
Well, for I would have to look up the plot again. I mean, well, people look, of course, first of all, into the overall continuum polarization and then polarization of different lines, right? And the deflagrations, for instance, because they are subject to these buoyancies and instabilities, are overall rather spherical, but they have, of course, a rather rich structure of large plumes in them. So the silicon line, for instance, could be more polarized than a continuum polarization that would be possible in this kind of model. And
I'm asking mainly about continuum polarization.
Okay.
From geometry.
Yeah. Right, so I mean, yeah, so continuum polarization, so from these Chandrasekhar mass explosions is actually predicted to be low, as seen in the observations, but observations also don't agree, right? So that you have some events where the polarization is higher than in others. So at least there's one, I don't remember the telephone number of that supernova, but there's one that compares still rather well to the merger simulation, because this had a higher degree of polarization than the standard Turbinate supernova. So most Turbinate supernova have a rather low polarization and seem to be better matched by Chandrasekhar mass explosions, but there are also some objects that seem to be fitted well by the mergers. So I can actually...
Probably it's some current result, but I don't think that continuum polarization was really observed in type 1a. It was like around less than 1%, around 0.5,
no,
which can be interstellar polarization.
Yeah, okay. Yeah. But yeah, I mean, that's a limit data, as you said, so it should be low, that's right, yeah. But yeah, okay, so we can look that up again in the paper. There was a recent paper by Mattia Bulla, so he had it on the archive like a month ago or two.
Last question, yes, Corinne? I have a very, very basic question. How do you determine observationally the delay time?
Oh, I don't know. Ask Alicia.
I mean, yeah, because I guess there are many hypotheses behind.
Yeah.
But the metallicity, the population.
Sure. Yeah. I mean, you look into the environment, and of course, yeah.
So it's not
It's not so solid, right? Yeah.
It's deduced
Yeah.
through a number of
Right.
hypotheses.
So actually, well, I mean, these are the latest plots that were in Danny Mao's paper. The earlier plots actually had huge error bars in the observations, and they are somehow gone now. I don't know why.
Yeah.
But the first plots I've seen of this actually had error bars that actually extended also in this direction very widely. And so the supernova rate seems to be better constrained now. The delay time, however, still has rather large error bars, as you see here.
The last question is? I wanted to ask about superluminous supernovae.
Yes.
The question actually is, it's also connected with observations, but so you showed some explanation, like rotation or magnetic field.
Well, this is not this is what people have speculated about. I didn't say that this is really an explanation, because we actually looked into this and it doesn't seem to fit. I just wanted to...
So you said that it cannot be more than 3 solar masses. It is written.
More than 3 solar masses? No, this well, chandrasekhar mass, I mean, yeah.
So how much, so if it's rotate or have very big magnetic fields, how much you can increase the chandrasekhar mass?
Well, so the mass that's still supported can, with differential rotation, can be 2 solar masses, so that's possible. At some point, however, the stars will not look like stars anymore, but they will be donuts. And then the question is, what would an explosion in a donut look like? Is this reasonable or not? And yeah, so that.
Tomorrow afternoon we will make a workshop for exploding donuts. Okay, I propose we move to quiz lectures. Thanks.